What Alan Turing might have discovered. I happen to have spent a large part of my life trying to figure out what sort of the implications of the big idea of computation are. And I've ended up sort of taking some of the ideas that I think Alan Turing pioneered and trying to see just how far those ideas can be taken. So I've mostly worked on three big things: Mathematica, Wolfram Alpha, and a new kind of science. And with Mathematica, I suppose in a sense, I was in some sense trying to finish what Alan Turing, following others, had started, which was to see how one can mechanize, make computational, the process of doing mathematics. And that's something where in building Mathematica, sort of my concept was to have these kinds of lumps of essentially mathematical or computational work be represented by this language in Mathematica, and to try and cover, as Turing had tried to cover with his Turing machine, make mechanical the process of doing mathematics. That's been sort of my goal over the last 25 years with building Mathematica. One of the reasons that I built Mathematica was because I wanted to use it to kind of explore this kind of notion of computation in a broader way. And I suppose I got into that through thinking about natural science, not really through thinking about mathematics, but through thinking about natural science. And kind of the origin of my work had to do with the following question. So we look at the natural world, and we know that there are certain scientific methods that allow us to explain things about the natural world, and particularly the leading paradigm for the last 300 years has been this idea of using mathematical equations to describe and model the natural world. And that's been something that's been, ever since Galileo and Newton, it's been a pretty successful idea that's allowed us to make all kinds of progress in studying the orbits of planets and all kinds of things in physics and elsewhere. But it's also clear that it hasn't given us the whole story, that there's lots of things in nature that are not well explained, well understood, well predicted and so on by pure mathematical equations. So the question that I started thinking about 30 years ago now was a question of, so if mathematical equations aren't the whole story, what else could we do? So if one is going to have a model for a system, it better be the case that that system operates according to some definite kind of underlying rules. The question is, what is the raw material that one should use to build up those rules? Is it, for example, the things that we have from mathematics, multiplication, addition, exponentiation, derivatives, integrals, things like that? Or could it be something more general? And so the key idea that I had was perhaps it can be something more general, and the sort of place where one gets those more general things is from computers and computation and computer programs and so on. The question was, can one make a program, something like a Turing machine program, that will describe what happens in a system in nature, rather than making a mathematical equation to do that kind of thing? So so that got me started in the question of, okay, if that's going to be the case, if there's going to be a program that represents some system in nature, what might that program be like? Well, the programs we're used to dealing with are these long, complicated programs that we write out of thousands, millions of lines of computer code for very specific purposes that we want to achieve. And it's not very plausible that nature has this million-line program that describes how some simple system works. The question is but then there's sort of a basic science question, which is, if we think about all the possible programs that we could imagine writing, we could ask the question, what do the simple programs out there actually do? Imagine sort of this computational universe of possible programs and just start asking, what do these programs typically do? Well, I started off looking at a very simple set of programs that are called cellular automata, and this is a typical example of one of these cellular automata. It just has a line of cells, each one is either black or white, and at every step, the color of each cell is determined by the color of the cell above it and to its left and right. So in this particular case, we start off with one black cell. We get some very simple behavior. We can keep going and see what happens here. We can represent the rule that's being used by that icon down at the bottom that says, for every cell and its left and right neighbors, what should the color of the cell underneath be on the next step? And we start off with a black cell at the top, and we just get this very simple pattern. So then the question is, well, what happens with other possible rules? So we can go on, we can change a bit in the rule. We find out that instead of getting a uniform black pattern, we get this checkerboard pattern. Maybe we change another bit in the rule. Here we get a slightly more complicated pattern. can continue that for a while longer, and we find out that that pattern, it's very intricate, but ultimately it's a very regular, nested fractal pattern. Well, at this point, we might imagine that there will be some general principle that if the rule is simple enough and the way it starts, the initial conditions are simple enough, then it must necessarily be the case that the pattern of behavior that we get is somehow correspondingly simple. But the thing that I realized a long time ago is that it's easy to just do an experiment to find out if that's true or not. And so sort of pointing my sort of pre-Mathematica at that time computational telescope into this sort of computational universe of possible programs, this is more or less what I saw. So this is the first 64 possible programs of this type that I described. Each one of these is a different underlying rule. All of them are just starting from one black cell. And there are all sorts of weird creatures in this kind of computational universe that we see. A lot of them are very trivial. They just, the black cell just stays the same and just goes down the page, or it slides to one side or the other. It makes little stripes, things like that. But if you look at this set of pictures, the most interesting one you see first is this one, Rule 30. So what does that look like? Well, let's keep running that a little longer. Here's what we get. So we're starting off from just one black cell. We're using that rule at the bottom there, get this kind of pattern. So when I first started working these kinds of things out, my assumption was that if you keep running it long enough, it will somehow resolve into something simple, or at least there'd be some fancy method for mathematics or statistics or cryptanalysis or something which would allow us to look at the pattern that we see here and recognize that actually that pattern came from some simple origin down here and essentially be able to crack the behavior of this particular system. Well, you keep on running it a while longer, you get a pattern like this, and over on the left you can see there's a certain amount of regularity that exists. But overall, this pattern looks surprisingly random. And through lots of efforts of mine and many other people's, the many features of this pattern have never been cracked. So for example, if you look at the center column of black and white cells here, it seems to be, for all practical purposes, completely random. It's random enough in practice that we used it for a long time as a pseudo-random generator in Mathematica. It's been a very successful pseudo-random generator. It's sometimes also used as a stream cipher for cryptography. So it's pretty weird that you can just go out into this computational universe of possible programs, and rule number 30 is something that is as complicated as this. It's something that's very much against our normal intuition that something like this should happen, because normal intuition is, if we're doing engineering or something, we want to make something complicated like this, we have to go to lots of effort to do that. But here it sort of seems effortless. Just rule number 30 in this computational universe just happens to produce something like this. Similarly, if we were to find a pattern like this in nature, we'd probably assume that that pattern had to be produced in some very elaborate way as the result of some long, elaborate process of natural selection and evolution or some other very elaborate thing. But again, we now can see that that's not the case, that in this computational universe of possible programs, things like this actually occur rather often. Well, I actually think that this fact is indicative of something pretty important about natural science. See, it seems like nature has some kind of secret that lets it make complicated stuff very easily. But we don't have that secret when we make technology and we do engineering. And so that means that typically, if you're shown two objects, one's an artifact, one's a natural system, it's still a really good heuristic that the one that looks more complicated is the one that's the natural system, because it seems like we don't have the secret that nature has that lets it make the complicated stuff that it makes. Well, I think this Rule 30 cellular automaton is kind of an indication of what that secret of nature actually is. See, when we make things with engineering, we typically always want to foresee the results of what our engineering processes do. And so we tend to avoid, we've sort of constructed our processes of engineering to avoid systems like this. But nature is under no such constraint, so it can just sort of go out into the computational universe, sample possible programs almost at random, and often find things like this. Well, so you can go and look at this computational universe of possible programs. You find all sorts of lovely stuff out there. It's easy to find such things. Again, this is just starting off from one cell at the top and just evolving with some simple rule, and it looks like a kind of very organic thing that's going on here. This is common stuff to find. Well, a thing that I got interested in is, okay, is this something special to cellular automata? Is this some feature of the way that cellular automata work with all their different cells and doing parallel computation and all those kinds of things? Or is it something that is a sort of more robust general phenomenon? Well, so I started looking at that actually after Mathematica came into existence. And one of the first sort of things to look at was Turing machines. So Turing machines are different from cellular automata because Turing machines have just one head that walks back and forth, being the place where the colors of cells get updated. Cellular automata work in parallel where all cells get updated at the same time. But so this is a typical Turing machine. This one is a three-state, two-color Turing machine. Starts off from a blank tape up there, and its head walks backwards and forwards, and it makes this kind of stripy pattern here. Well, so the question is, are there Turing machines that do complicated things like cellular automata? Well, you look at the first 4,096 Turing machines that have just two states and two colors, and actually nothing too exciting happens. The most interesting one is this one over on the right here, which is operates like a binary counter. So it's sort of counting up in binary. Well, you don't actually have to go much further in the space of Turing machines before you start finding things that are actually very much like what you see in cellular automata. So here's an example of one that is a three-color, two-state Turing machine, and the thing on the left is just the raw evolution of the Turing machine. The thing on the right is kind of a summarized version of that evolution where one's only showing those rows of the Turing machine where the head got further to the left or right than it's ever been before. Well, it's pretty clear from that right-hand picture that actually there's considerable similarity between what happens in this Turing machine and what happens in a cellular automaton. Okay, so that's kind of interesting. So how general really is this phenomenon? We can see it happens in cellular automata, it happens in Turing machines. If you're an enthusiast of register machines, it happens in register machines as well. If you're an enthusiast even of traditional kind of mathematical equations, turns out it happens there too. So like here are some partial differential equations, sort of the central things that get used in mathematical physics to model systems in nature, and the kind of thing that actually Alan Turing used when he decided to look at morphogenesis in biological systems. It's kind of always been slightly weird to me that Alan Turing didn't think about using Turing machine-like or cellular automaton-like systems when he studied morphogenesis. In fact, I found many years later that you can that in fact permutation patterns are modeled in a rather wonderful way by cellular automata. Can talk about that in a minute. But in any case, even if you look at that sort of bastion of mathematical physics, partial differential equations, these are some typical partial differential equations that you'll find in textbooks of mathematical physics. But if you just say, let's just search the space of possible partial differential equations, just like we search the space of possible cellular automata or possible Turing machines and see what's out there, it doesn't take long before you find things like this. These are kind of nonlinear equations that have the feature that you start them off from just some simple initial condition, and they pretty soon produce this very elaborate behavior. Now, the reason things like this were not well discovered in partial differential equations, for example, is it's really hard to know if these are the right answer, because partial differential equations are not well mapped onto standard digital computers. In order to solve these things on a digital computer, you have to make all sorts of numerical analysis approximations. And actually, you have to sort of turn this continuous system into a discrete thing that can be mapped onto a digital computer. It's always been a great test for numerical differential equation solving in Mathematica to see how far we can take these particular equations. But the point is that you can't really be sure that the complication that you're seeing in the behavior of these equations is a feature of the equations themselves, or whether it's just some sort of pathology of the numerical analysis scheme that you're using. Well, it's a different situation in something like the Rule 30 cellular automaton, because in the Rule 30 cellular automaton, the bits are the bits. There's no ambiguity, there's no approximation going on. It's just a deterministic system. It follows that rule at the bottom, and it makes this whole pattern of behavior. Once you've seen that in Rule 30, you can go back and realize that actually it happens in partial differential equations and things too. So, okay, so it's a fairly robust phenomenon that you can get this sort of very complex behavior even from very simple underlying rules. There's a question of how that relates to what we actually see in nature, and you can look at something like a snowflake pattern. And you can realize that actually the origin of that behavior is something that can be rather well modeled with even a very simple program, simple cellular automaton. There's a simple two-dimensional cellular automaton. These are the successive steps in its evolution that does a really rather good job at modeling many details of what happens in something like a snowflake. And you can go on and look at things that have been sort of mysterious features of, in terms of traditional physics, for example, like the randomness of fluid turbulence, and you can understand something about sort of what the origins of the randomness that occur in things like fluid turbulence are. You can even go on and look at something that's sort of closer to the Turing beat. You can look at biological systems and growth processes in biological systems, and you can ask the question, how complicated, how simple can the programs be that produce these kind of biological growth processes? When Turing looked at this, he looked at it in terms of partial differential equations. He could perfectly well have looked at it in terms of Turing machines, and he would have found all kinds of interesting things, I think. And what you discover is that, I don't know, if you're looking at, for example, leaf shapes, you discover that there's some very simple models that can reproduce sort of the diversity of shapes that you get there. If you look at, for example, another one of my favorites is mollusk shells, where it's actually a pigmentation pattern question, a little bit like Turing's cow pigmentation pattern, where now one of the sort of mysteries is that the pigmentation patterns of different shells are quite different. And if you look at, you can make shells grow in this very nice one-dimensional way where they have just sort of a growing lip, one-dimensional growing lip, where they put down shell and pigment on the shell. And you can ask, well, what happens if shells just sort of randomly pick possible rules for the row of cells that are on that growing lip? Well, then you would end up with different species of mollusks having patterns of behavior that correspond to different possible cellular automata, and you would see patterns that correspond to things like this. And you see here that there are little stripe patterns, and there are spotted patterns, and so on. And then there are those weird triangle sort of tent-like patterns. Well, if you actually go and look at the natural world of mollusk shells, you find stripes and spots, and bizarrely, you also find these tent-like patterns. It's just the same kind of thing that you see in this space of possible systems in the computational universe. So what seems to be the case is that what we're seeing in mollusk shells is sort of almost a random selection of different possible programs from this computational universe, and then the shells are essentially running these programs, and we get to see the results printed out on the shells. Well, you can go on and look at many other kinds of systems and discover that this idea that there are simple programs that underlie behavior of systems in nature is something that happens all the time and is rather a powerful feature of modeling in the natural world. But then you can go back and ask sort of a more fundamental question. Okay, we see this Rule 30 phenomenon. Why does this happen? What's really going on here? And so what I come up with is a thing I call the principle of computational equivalence, which in a sense is a generalization of Turing's ideas about universal computation. And essentially it works like this. So if we look at different possible systems, we can say that every one of these systems, where every one of these different, for example, cellular automaton rules, is performing some kind of computation. And the question is, how sophisticated is that computation? I mean, some of these things, the computation is pretty trivial. It's just leaving the input unchanged. Other ones, it's doing some other fairly simple computation. The question is, how sophisticated is the computation that these different, if we fed them different initial conditions, they would sort of run and produce some output. How sophisticated is the computation that's being done that goes from the input to the output? Well, this principle of computational equivalence, well, you might think that as you make the rules for the underlying systems more complicated, that somehow the sophistication of computations that they do would somehow progressively increase as the rules for the underlying system get more complicated. What the principle of computational equivalence says is that that's not the case. That as soon as you're above systems whose behavior is obviously trivial, then you get beyond a threshold at which the behavior, the computations that the systems perform are effectively always of equivalent sophistication. So it's not the case that above this threshold, you're just flatlined. It doesn't, as you increase the complexity of the rules, you can't go on increasing the sophistication of the computations. The computations are already of maximal sophistication. Okay, so this is sort of something that originally I came to for sort of empirical reasons. One can ask, Well, okay, so how would one get evidence for this particular hypothesis? So one prediction of this principle of computational equivalence is that it should be the case that any one of these systems that is not obviously simple should be capable of computations that are as sophisticated as anything. In particular, it should be capable of universal computation. It should be capable of more than that, but among other things, it should be the case that there exists some initial condition that can be set up that will make this system emulate any other computational system. In other words, this should be something that is generally programmable. Well, so is this actually true? Well, we begin to get a little bit of evidence about it. So, for example, this is one of these cellular automata. This one is Rule 110, and it started here from a random initial condition. And we see it has all these various structures running around. And you might imagine that these structures might be doing some kind of computation. Well, with much effort, one can show that, yes, indeed, that is the case. In fact, this particular cellular automaton, Rule 110, is computation universal. So of the 256 very simplest possible cellular automata, at least 4 of them we know so far are computation universal. Probably Rule 30 is computation universal, but we don't know that for sure yet. I'm pretty sure it is, but it hasn't been proved yet. Well, so it's sort of a remarkable thing that in this space in this computational universe of possible systems, we already know that some pretty low-lying systems, pretty simple systems are computation universal. You can ask the same thing in Turing machines. What's the simplest possible universal Turing machine? Well, when Turing set up his first universal Turing machine, it's a big, complicated, hacky thing. Over the years, people found slightly simpler universal Turing machines. But there's a question, what's the very simplest possible one? Well, we know that there is no Turing machine that with 2 states and 2 colors that can be computation universal. I showed before. This is sort of the pretty much the spectrum of different behaviors there, and you can show that none of these can be computation universal. They're all kind of showing fairly trivial behavior. If you go and start looking at sort of the next level of Turing machines with 3 colors and 2 states, for example, I showed before this one that you get to. So then the question is this particular thing universal or not? Nothing simpler than it. Everything simpler than it we know isn't universal. So this would be sort of the first possibility for a universal Turing machine. And this principle of computational equivalence of mine says that actually this should be universal. That would be good evidence. If it is universal, it's good evidence for this principle of computational equivalence. If it isn't universal, it's kind of embarrassing for the principle of computational equivalence. So it's kind of a place where, even in this very formal system, we get to do something a little bit like natural science, where we're trying to find evidence for things in this kind of way. Well, a few years ago, I decided what's the best way to figure out if this is universal. I decided I would put up a prize for somebody to prove or disprove that this is computation universal. And I actually thought this prize might be out for 100 years, not being figured out whether it is or isn't universal. To my considerable pleasure, after a limited number of months, a chap from Birmingham, young fellow from Birmingham, announced that yes, in fact, he'd solved this, and indeed it was computation universal. So that was pretty neat. Among other things, this is the simplest universal Turing machine. There can be no simpler, and this one is universal. So that's kind of nice to know that, you know, Turing started off in 1936 with a pretty complicated universal Turing machine. We've now got it down to this is the simplest one that can exist. It's also pretty interesting because it gives us a good piece of evidence for this principle of computational equivalence. Again, in the space of Turing machines, once one's got to ones which aren't obviously simple, one sees this kind of, one sees computation universality. Well, okay, so if we believe this principle of computational equivalence, what other implications does it have? So another one of its implications is a thing I call computational irreducibility, which is kind of a lower level version of the kind of undecidability of the halting problem and so on that Turing looked at. So the question is, if you have a system like this, for example, and you say, well, what's it going to do after 10,000 steps? Well, in the sort of traditional kind of mathematical science approach to things, the big thing you want is to be able to predict stuff. You know, if you have an idealized planet going around an idealized star, you don't want to have to trace sort of 1,000,000 orbits to find out where the planet will be. You just want to fill in the number of million and look up in a formula what the result will be. That's a case where one's effectively, by being smarter than the planet in some sense, one's able to computationally reduce the amount of effort that it takes to work out where the planet will be. So the question is, for a system like this, is there computational reducibility, or is this something different? Well, what this principle of computational equivalence implies is that there will be computational irreducibility. In other words, that to work out what happens after some large number of steps here, really the most efficient way to do that is just to follow the actual evolution of the system and see what it does. So that's something where it's saying that, when one studies systems, it's ultimately necessary to simulate their behavior. One can't expect to have sort of a simple formula that just gives one the result. Lots of implications of computational irreducibility there are implications about free will versus determinism. There are implications about practical issues about simulation. There are implications about undecidability and how ubiquitous it is and so on. But that's just another feature. Another thing to realize is that this principle of computational equivalence is supposed to apply to every kind of thing, whether it's a simple cellular automaton or whether it's a brain or something like that. And there's sort of an idealization that gets made typically in science, which is, our brains are definitely a lot smarter than the systems we're studying in nature. That's the usual assumption. But the principle of computational equivalence says that shouldn't ultimately be true. And that's sort of the fundamental reason that something like this can look complicated to us, because if we with our brains were always able to sort of outrun and outpredict and outcompute what this system was doing, we'd be able to recognize that there was sort of a simplicity to what was going on here. But the fact that this system is sort of equivalent in its computational sophistication to our brains is why it necessarily looks to us complex. Well, there are all kinds of things one can think about this. I'll mention one implication of these kinds of things is the question about our universe, for example. We can now see that from this rather simple rule we get this rather complicated behavior. So the question is, what about our whole universe? Could it be the case that our whole universe actually grows from something that is ultimately a very simple rule? Well, we know that our universe, so the question then is, okay, we've got our universe, it does all the things it does. If it's represented by some program, how long is that program? Is it 4 lines long? Is it 1,000,000 lines long? Is it a quintillion lines long? How big is the program? Well, we know it's not incredibly big, because we have some evidence it's not incredibly big, because there are actually definite laws for the universe. It could be the case that every particle in the universe just does its own thing and has to be represented by a different case in the program. That isn't what happens. And that's a fact that, for example, theologians a long time ago realized this important point about the universe, that there is order in the universe. They had their implications for that. But today the implication is the program for the universe can't be as complicated as it might be. So then the question is, well, how simple is it? And so then the question is, if we look in this computational universe of possible programs, where does the one for our universe actually lie? Is it one that is sort of at a low enough serial number that we might find it just by searching through possible programs in the computational universe, or is that absolutely hopeless? Should we do sort of reverse engineering of the actual universe to find it? Well, there are lots of things. It's sort of a long story how one can start thinking about physics in terms of simple programs. But one of the features of the physical universe being represented by a simple program is that if you're going to pack all that information about the universe into a tiny program, almost nothing about the universe that is familiar to us today will be visible in that program. So what's in that program will be sort of underneath space and time and so on. It will be something that is that has all those things sort of packaged together in some complicated way, and there won't be any place where you can see in that program the number 3 representing the number of dimensions of space or something like this. Well, I think there are a bunch of different ways one can represent sort of the underlying structure of such a program. A convenient one is to think about it as some kind of network of nodes, where every node is just it's all one knows is the connectivity of nodes. One doesn't know how many dimensions the thing is in. It's just this big ball of network. And you can assemble networks into things which in the large scale will be like one-dimensional networks, two-dimensional networks, three-dimensional networks, whatever. But in general, one could just say, well, the universe might be like a network. Something I realized recently that I think is kind of fun is if you think about the history of physics, one of the things that was an important step was the realization that Euclid's axioms did not necessarily govern the physical world. And the particular one was Euclid's 5th postulate that said that 2 parallel lines will never meet. It was realized by, eventually by Einstein and friends that that might not be true for physical space. And that's what led to general relativity and gravitation theory and so on. So the realization that sort of Euclidean axioms for things might not be valid for the physical world had an important implication. What I realized recently, if you read Euclid, the first line of Euclid is, a point is that which has no part. Well, I suspect that idea is wrong, and because what's going on, if this is what space is like at an underlying level, it's like saying, well, you've got a fluid like water and it behaves continuously, but at an underlying level it's a bunch of molecules bouncing around. That's sort of how space would work, and that means that there is no notion of an indivisible point. There's sort of structure of this kind that lies underneath kind of the usual notions of physical space. Well, okay, so you can go and actually start enumerating possible universes, and there's lots of technical detail about what's going on, but basically the idea is you just enumerate possible rules for how these networks might get updated, and you ask yourself, are any of these things like our universe? Well, a lot of them are obviously not like our universe. They have no notion of time. Space is bizarrely, infinitely exponential, and obviously not like our physical space. But it doesn't take that much time before you start finding ones where actually they're obviously not our universe. One is completely bitten by computational irreducibility, because as you start running these things, you run for 1 billion steps, it's flapping around inside your computer, and it's very hard to tell whether what it's doing corresponds to the actual laws that we know from physics or not. And clearly we can't get to run these model universes for as long as our physical universe has been running, because that's not something we could practically do in our computer. So you have to kind of hope for little pockets of reducibility in this kind of sea of computational irreducibility. Actually, I've made quite a bit of progress on these kinds of things, but and in fact, turns out you can derive special relativity, which is kind of non-trivial because in usual physics, that's something which is put in from the beginning. You can even derive many features of gravitation and general relativity from these kinds of systems. And you can start to see how various features of quantum mechanics arise. So it's kind of interesting, and it's, the big challenge is, could our physical universe actually be a simple program that's out there in the computational universe? In effect, could our universe be something like a Turing machine? I mean, this particular construction of these things isn't, on the surface like a Turing machine, but this to show that such a thing would reproduce our universe. It also implies that any universal machine could, in principle, reproduce our universe. There are all kinds of interesting questions. If we find that our universe is number 50,000, number 3,000, number 200 or something, in the space of all possible universes, that's a sort of an interesting Copernican moment, because we kind of think that from post-Copernicus, we kind of assume there's nothing special about us, that we can't be a special central, at a central place in the universe or anything like that. Yet in this computational universe of possible universes, if we could find our universe by just doing a search like this, it would imply that we were sort of at a low number in the computational universe. Anyway, so this idea of simple programs and what they do and so on has all sorts of implications. It actually has some really practical ones as well, which kind of are perhaps interesting to talk about. I mean, the one place where you can use something like one of these cellular automata, for example, is to say, well, let's use these as raw material to make models for things in nature. But another thing you can do is to say, well, let's see if we can use these things to make technology. And what is technology? Technology is typically taking what exists in the world and harnessing it somehow for human purposes. So a typical thing that we've done with materials, physical materials, is to say, let's go see what we find out there. We find magnets, we find liquid crystals, we find electro-optic substances, things like this. Each one of these, we then realize at some point, well, liquid crystals can be used for computer displays, for example. We're essentially mining what exists in the natural world and harnessing it for particular human technological purposes. Well, we can do exactly the same thing in the computational universe. And what happens there is that, for example, I mentioned that Rule 30 is a good pseudo-random number generator. You can go and look in the computational universe for things which are good things for doing certain kinds of image processing, or good things for doing fast function evaluation, or good things for doing network routing, all kinds of different things. And it's different from the usual practice of engineering, where you say, I've got an objective and I'm going to step by step build a program to achieve that objective. This is something where you're just saying, I've got this objective, now just go out into the computational universe and find something that satisfies that objective. Seems kind of crazy. If it wasn't for the fact that you don't have to go very far in the computational universe before you get really very sophisticated behavior happening, that would just be a crazy thing to do. It's kind of interesting to see in a lot of domains, you can kind of ask the question, where does the interesting stuff start to happen in the computational universe? So one example of that one can look at is, for example, mathematics. So, mathematics, there are axioms for mathematics. This is pretty much the axiom systems for all of mathematics that's practiced today. From these axiom systems, the 3 million theorems that are in the literature of mathematics have been proved. But you can ask the question, if you just look at all possible axiom systems, where do the interesting ones start happening? And this is kind of an idealized version of mathematics where possible axiom systems run down the page, possible theorems run across the page, and for every time there's a theorem that's true for a particular axiom system, there's a black dot. So the question is, where do sort of popular fields of mathematics actually lie in the space of possible mathematics, so to speak? Well, an interesting one case of that is, for example, Boolean algebra, logic. And you look at a logic book, you find that there are typical axiom systems, the ones written over there on the left. It's been known for 100 years that you can not have to use and or not. You can just use the NAND operator. That's how all computers work, to represent all logical operations. But then you can ask the question, well, in the space of possible axiom systems, what's the very simplest axiom system that corresponds to Boolean algebra, to logic? And it turns out it's this one here, which I found about 15 years ago now. It's about the 50,000th axiom system that you find just searching through the space of all possible axiom systems. And you can prove that. Actually in Mathematica today, it takes a few seconds to prove it. That's a version of the proof written out. That's an automatically generated proof of no great use to humans. But it kind of establishes that it's true. But so that's a case where we're sort of searching the space of possible mathematics to find ones that are useful, for example, for logic. And that we find the axiom system for logic. But you can do this in great generality. And I think one of the things we've realized is that computation, the idea of computation as an engineering matter is something that has grown up over the last 50 years or so. But that's only the beginning. There's more to computation than what you can build with engineering. And so what's happened so far is that we've seen this question of following the Turing machine and so on. We've seen this idea that you can program you can program universal hardware to do all kinds of things, but you have to go to all this effort to do that programming. There's actually a whole nother level of possibility, which is to just say there's this computational universe that is revealed to us by these computational systems, and in that computational universe there are all kinds of things that are useful that we can just go out and mine for ourselves. And my guess is that in the next 50 years, by the end of that time, vastly more technology will be produced by this methodology of essentially algorithm discovery in the computational universe than is produced by all other methods of engineering development put together. And we can see all kinds of, in our own sort of software development methodology, we've very much incorporated this. You can see it in lots of other places. You can see it in some artistic kinds of places. We had a project a number of years ago that exists on the web of where we generate musical forms by just sort of mining the computational universe of cellular automata for things which satisfy the criteria of certain kinds of musical styles. And it's turned out to be a rather popular website, actually bizarrely enough, among composers who are interested in finding sort of inspiration from this computational universe. One might have thought that the part the humans would be involved with is the inspiration part and the computer would be embellishing it, but actually it seems to be the other way around. And it's sort of interesting, it's actually kind of a Turing test type thing for music, that you can get these pieces that are a couple of minutes long and they sound pretty good, and they sound just as good as what humans produce, at least up to that length scale. So one of the things, so in this sort of computational universe of possible programs, what are the kinds of things that one can do there? Well, for me, an important thing that came out of thinking about this computational universe was coming back to a project that I happen to have been interested in since about the time I last saw Jonathan Bowen here, which was if you take sort of all this knowledge that exists in the world, how can you kind of organize it to make it computable? How can you set it up so that you can automatically get answers to questions that could be answered on the basis of knowledge that our civilization has collected? And so I thought that the only way to build a sort of a computational knowledge on that scale was to have something like an artificial intelligence, to have a brain-like thing where you'd have all the sort of characteristics of a brain and you'd start educating it just like you educate human brains and so on. So for decades, I kind of assumed that the only way to make progress in this kind of computational knowledge idea was to solve the problem of AI. Well, when I did this work about the computational universe, I realized that just can't possibly be right. That one had imagined that there was some sort of bright line between that which is intelligent and that which is merely computational. And I think Turing already realized that there wasn't such a bright line. People had imagined a much brighter line before he started talking about artificial intelligence around 1950. But I think that still, I at least had the point of view that there was some major sort of progress in computation that would be needed to have something which was sort of intelligence-like, that was beyond mere computation. But what this principle of computational equivalence shows us is that that better not be true. If the principle of computational equivalence is true, there really isn't a bright line distinction between that which is intelligent and that which is merely computational. And that's why, for example, when we start thinking about, something about extraterrestrial intelligence, and we ask, we get some sequence of bits from the cosmos, so to speak, that corresponds to some output of some very complicated thing like Rule 30. We ask ourselves, well, do we need the whole, a whole giant civilization to have grown up to give us that sequence of bits? Or could it be the case that somehow some, simple pulsar out there is kind of almost at random picking that kind of algorithm to make its bits? Well, I think so anyway, I realized that sort of this notion of intelligence shouldn't be merely, could be merely computational. So that led me to actually think back on this idea that I'd thought about for 40 years or so about 30 years at the time I started getting serious about it, but about computational knowledge and whether one could actually do something that was a little bit like what Turing imagined one might be able to do for artificial intelligence. In fact, Turing sort of talked about, what if one could take Encyclopedia Britannica and feed it to a computer? And could one make something that was sort of intelligent and knew things like humans do? Well, I decided about 10 years ago to actually try and do that. The result of that process is this thing called Wolfram Alpha, which, that's not it. I'm going to get to it. And so the idea of Wolfram Alpha is to try and sort of do the thing that one might have thought one needed artificial intelligence to do, and to be able to just sort of answer questions that answer sort of any question that one might that might be answerable by a human expert. So, for example, you can say, what's the integral of x cubed sine squared x, and you'll get the answer, and you'll get if it wakes up, you'll get all kinds of other interesting facts related to that particular integral. It's sort of the question is, how far can one go with this idea of computation? How far can one go in sort of in turning things into sort of pure computation? And I'm afraid this network is really slow here, but what's interesting is that one can sort of go beyond the merely the sort of obviously mathematical, so to speak, and one can realize that just lots and lots of things out there are computational. And kind of the notion of this Wolfram Alpha system is to try and be able to understand whatever kind of input one gives, whatever sort of thing tumbles out in terms of a sort of a human, sort of human thoughts that get translated into typing, and be able to work out what to compute things from that. So you type in something like this, and hopefully, if it wakes up, it'll figure out that that's probably a genome sequence, and it'll probably go and figure out the matches of that particular genome sequence on the human genome, and all those kinds of good things. And you can go. How about when will the sun set today? Let's see what it does if I ask that. I don't know if they probably figure that out. I don't know. Okay. So there it tells us that that time, and it tells us where the sun is right now from Oxford. It knows where we are from GeoIP information, so it's 3 hours and 5 minutes the sun will set. You can ask it. It's always fun to ask it the weather, because that's it's nice when you have a computer program where you can look out of the window and see if it's doing something reasonable, and that's telling us what's happening today, and it'll probably give us some weather prediction and things in a moment. It just started raining outside. I don't know. It's predicting the temperature's going to go down a bit. Oh yeah. Well, it says it's going to start raining right around now. It's but in any case, Wolfram Alpha is a big project, gets used in lots of places these days. It's sort of the goal is to try and sort of take as much knowledge as there is out there and make it computational, sort of achieve, in a sense, something similar to what Alan Turing thought he was trying to achieve when he talked about artificial intelligence, I think. And one can even start to talk to this, like if you have an iPhone 4S, there's this thing called Siri on it, which is powered by Wolfram Alpha. And if you start asking it questions, then assuming that the Siri system doesn't route your question to the wrong place, it will increasingly not do that. It will wind up in Wolfram Alpha, and it will wind up being able to get questions answered through this. So you can ask, well, is this how does this relate to things like Turing tests and so on? I mean, our goal has not particularly been to make sort of human-like dialogue happen, just as it's turned out that human-like dialogue is not actually what people want in many kinds of practical computational settings. I mean, when you go and buy tickets for something or something, it turns out that the visual presentation of what you can do is actually a lot more effective than the purely audio kind of pure linguistic thing that you get from a human. I think what we've realized is that for example, when Wolfram Alpha generates results, it gives this sort of report that's organized in this kind of visual way that turns out to be somewhat more effective than if you were just having a sort of Turing test, talking back and forth to the computer. But that's the kind of thing that we've learned from all that's happened in the computer industry over the last 50 years or so. The thing that's perhaps interesting is that sort of this notion that we can take sort of knowledge of the kind that humans have and actually make it computational, make it so that our goal is to make it so that if there's something that can be answered by a human expert on the basis of knowledge that exists in our civilization, that we should automatically be able to do it. That's something that finally, after all these years, is really becoming a very practical reality, and it's kind of fun as we sort of crunch through different sort of domains of human knowledge to see how many of them can really benefit from computation and from the idea that you can sort of use algorithms and compute things about it. Well, I should probably wrap up here, and I guess my main I think Turing, it's really interesting to see what Turing did in his life. He worked on a series of projects. It's kind of bizarre how many of those projects I have ended up interacting with at one time or another. Even I was amazed back in 1989, just after Mathematica had first come out, we wanted to make a sort of promotional poster of the zeta function, the Riemann zeta function. And so we had this thing that wiggles up and down, as the Riemann zeta function does. And I was looking up, who had computed these wiggles before, and it turns out Turing was the record holder for a while, based on a whole design that he'd made with cogs and gears and things to essentially do harmonic analysis of the zeta function. That was just one of many places where I've sort of ended up leading a parallel life to Turing's. Of course, it's, and I'm quite convinced that, for example, the things that I found sort of in the computational universe of possible programs, I mean, Alan Turing didn't, I think, ever actually simulate a Turing machine, but he probably would have done eventually. And I think he, you know, the intuition of everybody, Turing, von Neumann, everybody, and even people like me, was that this phenomenon that, that if you had a simple program, it should do something simple. That was the intuition. And you can see that I don't think Turing really addressed that issue. Von Neumann certainly addressed that issue and very much came down on the side of if you want to make something complicated, it has to be really complicated. That's why he invented, when he was trying to do mathematical biology, he invented this immensely complicated thing to do self-reproduction, even though that's utterly unnecessary. But he didn't realize that it could be unnecessary because he just had this intuition that if you want to make something as complicated as that, you have to go to all this effort. But in any case, it's so I suppose that my own view is that, you know, it's great that Alan Turing kind of seeded this whole direction of computation. It's also, you know, he died 5 years before I was born, and that was for me that was a good deal because that meant that I could get to discover all kinds of nifty things about the computational universe that probably would have been known 20 years earlier if Alan Turing had lived longer. So anyway, that's so I should probably stop there. Thanks very much.